Hello. Yes, I'm audible to all.
Yes, sir,
Hello.
audible.
Good afternoon to all. Hello.
Good afternoon, sir.
Yes, I'm
Very good
audible to
afternoon,
all.
sir.
Yes, sir, audible.
Hello.
Yes, sir.
I'm audible to all.
Yes, sir, you are audible. Screen is also visible.
Is the slide is visible?
Yes, sir, visible.
Yes. Hello. Is the screen is visible to all?
Yes,
Yes,
sir,
sir.
visible. Screen is
Yes, sir, it's
visible.
visible.
Okay. Is the slide is moving now?
Yes, sir, it's moving.
Okay. So today we'll discuss actually. So we have completed the part transistor and the different mode of transistor configuration and all the details working of the part transistor. So today we'll start actually. So we have completed also part JFET junction field effect transistor, and today we have to read or we will discuss actually field effect transistor, that is FET. Okay. So all of you know the field effect transistor is simple. Uh, just it is a semiconductor devices, and this is simple or this is just like a part BJT, which can be used as an amplifier or a switch. Okay, i'm a, I'm audible to all.
Yes,
Yes,
sir.
sir,
Hello.
audible.
Yes, sir.
Okay, so like BJT, FET is also a part 3 terminal device. However, the principle of operation of FET is completely different from that of the part BJT. So in the case of BJT that you may mark, that is current is due to the part both the flow of the part both the charge carrier. It may be due to the part actually both the part electron and hole. But in case of the part FET, you can find this current may be due to only one type of charge carrier, and that is why it is called part unipolar. Okay, so the principal operation of FET is completely different from that of the part BJT here. So the name field effect is derived from the fact that flow of the current through conducting region and is controlled by the part electric field. That is why we call the, so this is the part speciality in the part FET, and you can find this is a part, this simple current will control through the part conducting region, and this is controlled by the part the applied electric field, and how this electric field applied. So we will be discussed in details. Okay. Now, coming back to the part types of FET you can find. So based on the construction, the FET can be classified into two types. One is called junction field effect transistor, that is JFET, and the other is called the part metal oxide semiconductor or metal oxide semiconductor field effect transistor, or that is called part MOSFET. Okay, and this MOSFET again is also known as a part insulated gate field effect transistor, that is called IGFET, or metal oxide silicon transistor, that is called part MOST. Okay, so this is the part classification of the part FET like JFET and MOSFET, and this JFET will be part again classified as your part N channel FET JFET and P channel JFET, and similarly MOSFET is also part classified into deflection MOSFET and also the part enhancement of MOSFET. So we'll discuss actually in JFET in both N channel and also the part P channel, and also in part MOSFET, both the things we have discussed, the depletion and also the part enhancement MOSFET here. Okay. So before going to the part detail, let me talk about the part, the special, some features of the part FET. Okay. FET is a part simple voltage control device because output current is simple controlled by the part varying the part input voltage. All of remember, this FET is not a current control device, but it is a simple voltage control device. FET is a unipolar device because the current conduction is only by majority charge carriers. Okay, and the three terminals of FET are basically named as a part drain, source, and the gate. Okay, and that you can symbolically represent throughout the part this representation as D, S, and also the part G. Out of these terminals, gate terminal act as a part controlling element. So this gate will actually part serve as a part simple controlling element here. FET is a part is more temperature stable FET is part more temperature stable as compared to that of the part bijunction, or that's a part bijunction transistor. Okay, so this is also part another unique features of FET as compared to part BJT. So FET has very high input impedance, typically in the range of several mega ohm. Okay, so where we're applying the part simple the part input. So this input section has high impedance. Okay, and it is part basically some several part mega ohm. FET has higher input impedance than that of the part BJT. So FET is preferred in amplifier where high input impedance is part required. Basically, when you require the part high input impedance, so we can choose for the part FET as compared that of the part BJT actually. Okay, now so let's APDs are part require less space than that of the part BJT. Hence, they are part preferred in integrated part circuit actually. So basically, APDs are part simple assembled to the part integrated circuit. Okay, am I audible to all? Hello.
Yes,
Yes,
sir.
sir. Clearly audible.
Okay. Okay. Now let me come back to the part actually part junction filled transistor in detail actually. So depending upon the part majority carriers or charge carriers, okay, because you know there is as I already told part mentioned P type and N type or means P channel FET and N channel FET. So in P channel FET you can find holes are the part majority charge carrier, and in N channel FET you can find the majority charge carrier part electron. So depending upon the majority carrier, the FET has been classified into two types. One is called N-channel JFET with electron as a majority charge carrier, and P-channel JFET with the holes as a part majority charge carrier. So you can see the part this construction. Okay, this is the part construction of a N-channel FET. All of you can mark this is the part N-channel FET where N is the part main substrate and P is the part just like your part two the part the two sections or the part load of region. Okay, then you can find so this end part this left side this is called the part gate terminal, and this is called the part omi. It is called symbol the part. Yes, this is a part pair. So within a part N channel substrate, so the P and the part this is a gate, and this is called the part source here. Okay, so this N channel actually act as a part a heavily substrate where you can find the major charge carrier part electron, and this is the part basic symbol uh, of a part N channel FET. Okay, N channel FET as the major charge carrier electron. So you can find this is the part domain, this is the part drain, this is the part source, and this is called the part gate actually. So naturally, gate is made up of a part positive type, okay, or that is called part P type. So it consists of a part N type bar. So this is a part N type bar, okay, which is made up of silicon. That means a part N type silicon actually made up of a part substrate. Ohmic contact, right? Terminals made at the part two ends of the bar. You can see, okay, made at the two ends of the part bar are called source and the part drain actually. So this is called the part drain, and this is called as part source actually. Okay. Hello.
Yes, sir.
Hello. Am I audible to all?
Yes, sir. Yes, sir. Audible, sir.
Okay. Now you can see here. So this is the part simple. The part you can this is the part construction details. So this is the part internal FET. These are the part the metallic contact. This is called the drain. This is source, and this is part gate. Okay, and this is the part symbol. So this has the N channel FET. So I must put the part arrow mark towards the part base here. Okay. Now it consisting of N type bar which is made up of silicon. Ohmic contacts made at the part two ends of the bar are called source, and this is called a part of the source, and this is called a part drain actually. Then what is the source actually? The terminal. So this terminal is connected to that of the part negative terminal of the part battery. Okay, that means here you can find this part N channel or this part. Yes, you can find. So this terminal is part connected to that of the part negative terminal of the battery, and electrons which are the part majority carriers in the N type bar enters the part bar through the part terminal actually. Okay, so you can see this is a part gate. So gate, the function of the gate is it is simple control the part of supplied field, and this is called drain, and this is called the source, and this source is basically connected to the part the charge carriers which has to be allowed to the part pass to the part this a part n channel FAT here. Okay, so this terminal is connected to the negative terminal of the part battery. Then you can find electrons which are the majority carriers in the n type. Okay, the n type bar, then the bar sorry n type bar enter the part bar through this terminal. Actually, what are doing actually, if you can go to the details of this construction, then actually you can find part uh, this so this source terminal is connected to part the negative terminal. That means here you can find this part negative terminal. Okay, okay, and electrons which are the part moving as the carriers in the part n type bar enter the bar through its part terminal actually. Okay, here. Okay, now okay, now I'm coming to the part actually part drain. So which is the part upper terminal? This is called the part drain. Okay, so this terminal is connected to that of the positive terminal per battery. The majority carriers leave the bar. Okay, through this terminal actually. Okay, so this is part one of the advantages may be concept for the part n channel FET. Okay, similar gate is part, so it is a heavily doped p types silicon is different on both the sides of the part n type silicon, but silicon bar by which the part p junction are for p junctions are get formed. So these layers are joined together are called the part gate actually. Okay, okay. Now I'm coming back to that of the part channel actually. So this is I've told the part this is a part simple channel actually. So n type substrate to the p type channel. That means this channel is get formed from a part source to that of the part drain actually. Okay. Now I told the per gate and also the per the channel. So you can find the this channel is a per simple thin region between the two P gate, and it's called the part the channel. Since the channel is part in the N type bar, so the FET is also part known as part N channel FET. So just I have discussed in the part in details in the part above actually. So now coming to that of the part construction, the is construction or the structure and the part symbol of the P character P channel FET. We have seen the part N channel FET, and here you can find symbol the part P channel FET. Okay. Okay. Now I'm coming to the part construction and the symbol of the part P channel FET, because you are completed part N channel. In the similar way, you can find in the P channel FET. So this is a part of P type substrate, and part in the side that you can find N. So this may be create a part N channel part FET with the P type substrate as the uh, is as the uh, main component of the part this FET here. So this is the part symbol in the mark. If you can see, there is a part the arrow mark is for inwards, but here you can find n channel is a part simple outwards here. Okay. Now the device is part made of P type bar with two N type gate as shown. Okay. 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 Okay, you can see. So the device is part made up of P-type bar with the two N-type gate, just opposite to that of the part N-channel FET. Okay, and the N-channel FET is the part similar also. Okay, so the only difference is that in N-channel JFET, Okay. Is the slide is moving? Hello.
Yes, sir. Slide is moving, sir.
Yes, sir. Move.
Okay. See. So now let me put this the part construction of the part P channel and the part N channel FET or the structure. Let me go to the now part operation of the part N channel FET. As already I have told you, so the FET can operate depending upon the part its input voltage, just not like the part BJT. So we have to be discuss actually this operation at the different situation. So first we can discuss the operation N channel FET, that is static characteristic of the part JFET. So when VGS, all of you see, this is get to the part source voltage is zero. Get to source voltage part, here you can find. Okay, see. Yes. See, so when so initially that we have to first consider the part VGS. Okay, that is a gate to source voltage with zero. You can see also part in the upper diagram. So this is gate, this is a part source, and this is a part drain. So initially that we have to put the part gate source voltage will be zero. Okay, here when VGS is equal to zero, and the circuit symbol for the N channel FET will be what now will be modified from that previous one, from this one to your part this one here. Okay, so when VGS also when you can find VGS is zero, the circuit symbol for the part JFET will be this like this will be looks like this. Then the when VGS is equal to zero, that means when you can analyze our VDS is also equal to zero. When VGS is equal to zero, then you can find also part VDS is also zero. That is when the voltage is applied between uh, drain and that of the per source and the gate, and the gate and the per source, the thickness of the per depression region move. Yes, you can find here gate and source, the thickness of the per depression region is round around the PN junction is uniform and shown will be part this diagram. You can see when VGS will be zero, that means I'll put will be zero, VGS zero, then automatically the VDS will be part zero, because you know this is a transistor. So when the gate source voltage zero, there is no current flowing to the part drain actually. Okay, the VDS is zero. When no voltage applied between the drain and the part source and the gate and the source, the thickness of the deflection region is part around the part the PN junction. Okay, that means the thickness of a part, the thickness of the deflection region. So which is the deflection region? This is actually the part depression region. This region is called the part depression region, and as there is no current flowing through this, so naturally the depression region became part more thickness. Okay, is uniform and it can be part shown as in the part figure. So when VDS will be part zero and VGS is part decreased from zero, okay, then what you can find in this case the PN junction are uh, yes, the PN junction is the part are the reverse biased, and hence the thickness of the part deflection region is part simple increases. Just you can see when VDS is equal to zero and VGS is decreased from zero, is not actually exactly zero. VDS or VGS is part simple, but decreases part gradually or decreases to zero. Then you can find in this case the PN junction are reverse biased, and hence the thickness of the part deflection layer remain increases, or the region also part simple increases here. Okay, now as VGS is part decreased from zero, okay, the reverse bias voltage across the PN junction is increased, and hence the thickness of the part deflection region in the control, so in the channel will be the part the two depressed region make contact with each other. So what will happen actually? So as VGS is for decreases from the zero, the reverse voltage across the PN junction is increased, and hence the thickness of the uh, depression region in the is in this channel until the part the depression region or make contact with the part each other. So we cannot realize the proper operation. So till the part this will not actually combine. Means the part gate source voltage and also the part the drain source voltage. So now we can find when VGS should be 0, but the VDS is part increases from the part 0 actually. Okay, so you can find, so drain is a part positive with respect to the source with VGS is equal to part 0. Now the image now the majority part carriers in the electrons, okay, flow through the part n channel FED, okay, from source to part drain. Therefore, okay, okay, you can see. So therefore, the conventional current ID flows from the part drain to that of the part source, and the magnitude of the current will depend upon the part, depend upon the uh, yes, depend upon the part this of fact depend upon the factor. So which are uh, which are act as also part the part resistor circuit inside the FET actually. Okay, as you know, the FET is a current part simple the rheostat or the variable resistor. So according to that, you can also part change also. Then because of the part resistive of the part channel and the applied voltage VDS, there is you can find there is a gradual increase of the part positive voltage among the part channel from source to part that of the part drain actually. Okay, then you can find here. So this is the part region. What I've told the part the operation. This is the part gate. This is the part drain. This is the part source. So when the current will flow through the part allow to flow through the part this where, then you can find this is a part P channel and this is a part and this is a part N channel FET, because N channel FET P type of part substrate. Okay. So you must find as VDC also part increased. VDC part this VD is okay. So as VDC is part simple increased, na, the cross sectional area of the part channel will be part reduced at a certain value of the VDS. The cross sectional areas of the volume, mm, the cross sectional area at the P becomes a part minimum. All of you can see here. So when the VDS will be part increased, the cross-sectional area of the part channel will be reduced. So which one? The BDS means the part when the drain to source voltage part simply increased, the cross-sectional area of the part channel will be reduced here. At a certain value of the BDS, the cross-sectional area at B becomes a part minimum, because when the BDS is part increased, then actually you can find this channel became a part, the channel will become reduced, and you can find the cross-sectional area at also became at B also part became very small. At this voltage, the channel is part you can set to be pinched off, and the corresponding VDS is called pinch off voltage actually. Remember. So what I told, you can find as VDS is part simple increased, then the cross-sectional area of the channel will be part reduced as a result or certain value. VDS the part the cross-sectional area at B became support minimum. This one. Okay. Okay. So at this stage, the channel is said to be part pinched off, and the corresponding is called the part pinch off voltage. You can see now when I can plot the part actually VDS versus ID for the different value of the part VGS, I must find the nature of the graph of the part this uh, FET would be looks like that. You can see with the increase of the part gate to source voltage, that you can find this is gradually goes on part increasing from the part negative that of the part positive here. Okay. Now you can find in this graph there are part two region. One is your part ohmic contact, okay, and the other is called the part, yes, what you can find. So you can find here. So when visual part increases negative, sorry, decreases the part negatively, that is -3 -2 0, then you can find after that after the value became part saturate here. Okay. Now then as the VDC part simple increases from 0, Then ID increases part along the part OP. So the region from the VDS is equal to 0V to VDS is equal to VP is called the part ohmic region actually. When VDS is equal to part VP, you can find ID becomes a part maximum. When the VDS is part increase beyond the part VP, the strength of the pinch of region increases, and hence there is part no further increase of the part ID. You can see when you can put the VDS is equal to 0, you find the channel width part decreases, and you can find there is less flow of part charge carrier takes place. Okay, but when VDS is equal to part VP, that the ID becomes a part maximum, and when VDS is part increase beyond VP, the length of the pinch up again in region increases. Hence, there is no further increase of the part value of the part ID actually. At a certain voltage corresponding that of the part point B, this one, okay. Okay. So now from the part from this we can find from this characteristic curve we can have seen that the above pinch of voltage at a constant value of the VDS ID increases with increase of the part VGS. You can see also, you can realize -3, -2, -1 and also part 0. Okay. So from this graph at a certain voltage corresponding to the point B, ID suddenly part increases. You can see. Okay. Now, at a certain voltage corresponding to the part point B, ID suddenly part increases, and this effect is due to the part. Yes. Okay. So here you can find this effect is due to the part avalanche multiplication of the part electrons caused by the breaking of the covalent bond of silicon atoms in the okay. So when VGC is part negative, I told the part three different cases when it is part less than 0, when it is equal to VP, and you can find when VG is part negative, VDC is also part increased here. Okay. So when the gate is part simple maintained at a negative voltage less than that of the part negative cutoff voltage. Okay. So the reverse voltage across the junction is part again the part future. Okay. So next you can find in junction part further. So further increasing hence a negative value of VGS. Okay. Okay. So from this curve, it is observed that the above pinch of voltage at a certain constant value of the VDS ID increases with the increase of the per voltage VGS, and hence you can find JFET is suitable for use of the per voltage amplifier similar uh, to that of a per transistor amplifier. As like the transistor amplifier that we are applying the part, this similarly the FET can also per apply also. Okay. Now, what are the characteristics of the per junction field effect transistor? So in a JFET, the drain current ID depends upon the drain voltage VDS, and the gate voltage is per simple per VGS here. So what I call actually so to discuss the characteristic of the part FET, in a JFET you can find the drain current ID depends upon the drain voltage VDS. Okay. And the gate voltage also per VGS. That means the part this current will depends on the part both the part VDS and also the part VGS. Okay. So any one of these part variable may be fixed at the and the relation between the part other two may be part determined. And this relationship now determined by the part three parameter, which are like a part transductance, okay, mutual conductance, and also similarly you can find the part amplifying factor, and also you can find the part drain resistance here. Okay. Now, okay. Now, so in JFET, the drain current ID depends upon the drain voltage VDS and the gate voltage of part VGS. So any one of these variable may be part fixed, then the relation between the other two are the simple determined, and these relations are determined by the three parameter which are referred, that is called for is transductance, okay, or mutual conductance. So how you can calculate the transistance in the this curve actually what you can shown here, okay. So this voltage actually, then you can find here, all of you see, okay. So this transistance you can find actually, it is the slope of the transfer characteristic curves and denoted by the GM. So this is defined by change in the drain current and to change of the gate source voltage at constant VDS, okay, or that I can add delta ID by delta VGS, okay, when VDS is called constant. All of remember this may be short questions, okay. It is the ratio of the small change in the drain current to that of the corresponding small change in the gate voltage at a constant drain voltage, and it has the unit of the conductance, that is called the 1 by ohm, or that is called the mho, okay. Then that similar the drain resistance RD, it is the reciprocal of the slope of the drain characteristic, and it denoted by the RD actually. So RD is equal to change in the drain source voltage by the change in the drain current at constant VGS, okay. Similarly, the amplification factor mu is denoted by the mu, that is equal to change in the drain source voltage to change of the gate source voltage, okay, at a constant ID here, okay. Similarly, that if we can, so these are the small, these are the all three parameters which are defining the characteristic of the JFET. So what is the relationship between them? So as ID depends upon the VDS and also VGS, so the functional equation can be expressed as the ID. That means ID, I can say ID as a function of both the VDS and also the VGS here. If the drain voltage is changed, okay, it changes by small amount from VDS to your VDS plus delta VDS, and the gate voltage changes by small amount from VGS to that of the delta VGS, then the corresponding small change in ID may be obtained by applying Taylor's theorem with neglecting higher order terms. Thus, a small change in delta ID is given by delta ID is equal to delta ID by delta VDS at constant VGS into delta VDS plus del ID by del VDS into delta VGS. Now, if I can divide the both sides by the VGS, that means delta ID by delta VGS is equal to delta ID by delta VDS into delta VDS by delta VGS. Then I can find also delta ID by delta VGS here, plus delta ID by delta VGS, okay, at constant VDS here, okay. So since if ID will be constant, drain current constant, then ID by delta ID by delta VGS should be 0. That means this part will be 0. Hence you can find that you can see, so this left hand part 0. So 0 is equal to your delta ID by delta VDS as constant VGS into delta VDS by delta VGS at constant ID plus delta ID by delta VGS, okay. Now substituting the value of the partial differential equation coefficients, we got that we may get, this is nothing but a as we have defined the these parameters, this is 1 by RD and this is minus mu plus a GM. But as you know, GM is equal to mu by RD, okay. Hence mu is equal to RD into GM here, okay. Now therefore amplification factor mu is the product of the is the drain resistance RD and that of the transconductance GM. This may be a complete long question with our is FET, its construction, okay, the characteristics and the different FET parameters and the relationship between them, okay. Now I just I put the some problem actually that you can find. So this problem you can see this is a small electrons problem that may be current corresponding to FET that you can find. Okay. Now, expression for the saturation drain current or the transfer characteristic of the part JFET here. Okay. So from the transfer characteristic, VDS is maintained constant and at a suitable value greater than that of the part pinch of voltage. You can see that we have just now draw the part characteristic between ID versus the part VGS. Okay. So you can find this part the gate voltage VGS. Okay, is decreased from the part 0 till ID is part reduces to part to 0 actually. Okay, so if you can see, it is decreases it to part 0 till the part ID became the part also reduces to part 0 actually. Okay, so this is the part transfer characteristic of the JFET. Similarly, the slope of the transfer characteristic vary nearly per parabola, and it is found that the characteristic is approximately represented by the part parabola. IDS is equal to IDSS into 1 minus your part VGS by VP whole square here. So IDS is part saturation drain current. IDS is the value of the part IDS when VGS is equal to 0, and VP is the part simple pinch of voltage. Okay. Now, if I can differentiate for this equation 1 with respect to that of the part delta with respect to VGS, we must find delta ID by delta VGS is equal to IDSS into your part S into 1 minus, so as a square na, so 2 into 1 minus VGS by VP into minus 0 part 1 by VP here. So we know that Gm is equal to trans conductance, that delta IDS by part delta VGS where with VD constant. So I may put use this value over here, then I can find Gm is equal to minus of part 2 IDSS by part VP or into a part 1 minus VGS by part VP here. Okay. Now from this equation 1, again we can find also that 1 minus VGS by VP is equal to square root of part IDS by part IDSS. So now absoluting or substituting for this value in part equation 2. Okay, if I substitute this value, then I must find Gm is equal to minus of the part is this. Okay, by your part VP. Okay, suppose when VGS is equal to 0, then you can find Gm at that time also equal to Gm 0. Okay, and then from the part equation 2 you can find here, you can find this is not actually Gm, rather you can find this is Gm 0 is equal to minus of 2 IDSS by part VP here. Now from equation 2 and that of the equation 4, I may write Gm is equal to part Gm 0. Okay, you can find Gm 0 into 1 minus VGS by part VP here. Okay, so slope of the part transfer characteristic is simple here part is, you can find at IDSS is how can find that Gm is equal to minus 2 into square root of the part IDS into part IDSS by part VP, or you can find delta IDS by delta VGS is equal to part this much here. Now if I substitute the part delta IDS is equal ID is equal to delta is equal to IDSS, then I must find del IDS by delta del VGS is equal to minus 2 IDSS by part VP, or you can find IDSS by minus VP by part 2, or if I can part simplify here, then you can find also if you can take the part reciprocal of the part left side, then you must part get it here. Okay, so this equation shows that the tangent to the curve, okay, to the curve at the IDS is equal to IDSS, okay, and VGS is equal to 0, will have an intercept at is equal to minus VP by 2. So what the graph that you can find it here, this is called find the part minus VP by 2. When the tangent drawn to the part IDS versus VP curve, it has a part intercept on the part VP curve on the VP line at minus VP by 2 here. Okay, then okay, so this equation shows that the tangent to the part curve at ID is equal to IDSS, okay, part yes VGS is equal to 0, will have an intercept at part minus VP by 2 on this axis of the part VGS. Therefore, the value of the VP can be found by drawing the part tangent at IDS is equal to IDSS, and which at also VGS is equal to 0. Okay, that means the tangent what I have drawn that I can plot at part this value, and I can find
at that value, that is the part, the intercept at the VDS is equal found to be part minus Vp by 2. So the gate source voltage the gate source cutoff voltage VGS off on the transfer characteristic is equal that of the part pinch off voltage Vp. On the drain characteristic, that is Vp and Vp is equal VGS off. Therefore, ID is equal to IDSS into 1 minus of VGS by part VGS is square. Okay. So as like that, we calculate it for simple here for is VGS by Vp square. Similarly, that you can also get this graph also or this expression also. Okay. Now relating to part this, actually I have done also for some problem here that you can check. Okay. Now I'll be go for the comparison of JFET versus the part BJT. Okay. Hello.
Yes, sir.
Yes.
I'm audible now?
Sir. Yes, sir. Audible.
Okay. 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 Now let me go to the comparison of JFET versus a part BJT. Okay. So FET operation basically you can find depends upon the part the flow of the measured charge carrier. But in case of the part BJT, so that since it is only depends upon the measured charge carrier, I told you, or we basically for term this is called the part unipolar devices. Where BJT operation depends on the part both the minority and the measured charge carrier, so it is called the part bipolar device. Again, as the FET has no junction, and the conduction is part through N type or P type semiconductor material, FET is part less noisy than that of the part BJT. Maybe short question, why FETs are part less noisy? Because due to as the current is flow through the part channel, there is no part junction, so that is why it is part less noisy than that of the part BJT. As the input circuit of FET is reverse biased, so FET exhibits a part much higher input impedance and lower output part impedance. So FET can act as an excellent buffer amplifier, but the BJT has a low output impedance because its input circuit is part forward biased actually. Okay. Similarly, another is part FET is a part voltage control device, where BJT is a part simple current control device. So then FETs are part much easier to fabricate as particular suitable for ICs because they occupy part less space than that of the part BJT actually. FETs are part more temperature stable than that of the part BJTs, and BJTs are simple cheaper to that of the part to produce than that of the part FETs. Okay. So these are the part some of the for the comparison between JFET and also the part BJT. Now you can find some of the applications like FET is used as a buffer in measuring instrument. Then FET is part used in part RF amplifier. Okay. So the input capacitance part low of FET. Okay. FETs are part used in the part cascade amplifier in measuring and test the part equipment. Okay. So these are the part some of the applications you can find also that I've written. Okay. Now will we go for the part MOSFET? Okay. So what is that part MOSFET actually? So this is also one type of part one transistor, that is a metal oxide field effect transistor. Okay. Or you can sometimes you can see also the part yes most you can see also. Okay. So you can find 1 minute. Okay. So the metal oxide semiconductor field effect transistor is an important semiconductor device and is widely used in part many circuit applications. Okay. So now most of the part instruments are part simple operate on the part or that is working the part MOSFET. Okay. So the input impedance of a MOSFET is much more than that of the part JFET because a very small gate leakage current is part simple established here. Okay. But in case of the part BJT, you can find there is a part large amount of part. Yes. Hello.
Yes, sir.
Hello.
Yes, sir.
Hello. Yes.
Hello, it's audible, sir.
Am I audible to all?
Yes, sir. It's audible.
Hello.
Hello.
Pavan.
Yes, sir. It's audible, sir.
Okay. Please respond me actually. Okay. So here you can find the input impedance of MOSFET is much more than that of the per JFET because very small gate leakage current is here. So naturally you can find the input impedance of the MOSFET is much more than that of the per JFET due to the part a small gate leakage current. Like JFET MOSFET as gate, source and per drain MOSFET is also called integrated gate field effect transistor. Okay, IGFET, or that is also called as a part MOSFET because the gate of the part MOSFET are part insulated from the channel. Okay, so here you can find MOSFET is part classified into two type. One is called enhancement of the part type MOSFET, and the other is called the part deflection type MOSFET here. Okay, then what is the basic principle you can find that on which the part MOSFET is actually operate by applying a part transverse electric field across across an insulator deposited in the per semiconductor material. Okay, by which you can find the thickness and the hence the resistance of the per conducting channel of a semiconductor material can be controlled. As you can find, there is a controlling channel per gate form. So naturally, this channel is per simple get controlled by the per semiconductor. Okay, in a deflection MOSFET, you can find the controlling electric field across or a per insulator. Okay, 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 you can see. So in a depression MOSFET, the controlling electric field for is controlling electric field are simple reduces the part number of major charge carrier available for the conduction. Whereas in the enhancement, you see, just I told the part there are two type of part MOSFET. One is called deflection and other is called part enhancement. So in the deflection MOSFET, they actually find the controlling electric field part is reduces the part number of major carriers available for the conduction. Whereas in the enhancement MOSFET, application of part MOSFET, application of part this electric field causes an increase in the part number of majority carrier in the conducting region of a transistor here. Okay. Now I'll detail discuss actually the part this enhancement type. Okay. So before going to the part enhancement type, in enhancement type first you can see this is the part enhancement type MOSFET actually. Okay, and this is the part you can see this is a part n channels are there. Then a p type substrate is but very small amount of p added here. Then this is a part oxide layer, and over which you can find a gate layer. This is drain, and that is the part source here. Okay.
Hello, sir. Not audible.
It's now audible.
Now audible.
Okay. See, so this is the construction of the part enhancement type the part MOSFET here. So you can find this is the part uh, for the enhancement type of the part MOSFET. So here you can find this is a part simple n channel FET, and we are just added a part a small amount of the p type that is as a substrate. This is one the part is this is a part a dumping very small amount of dumping is actually performed on the part n channel FET, and you can see that is called the part insulated oxide layer, so for which it is called as a part insulated IGFET or insulated gate field effect transistor. That means the gate is simple get insulated from the per channel, and this is the part drain, and this is the part source, and this is the part symbol. So in all other cases you can find this is attached, but here you can find this is part not attached, and you can see one peculiar thing. So for arrow mark, this is for simple here for N channel FET na. So MOSFET. So you must find the arrow mark is towards the part this base always. Okay. So just mark the part the difference or the part symbol of N channel FET nicely. Okay. Here you can find. So this figure shows the construction details of the part N channel MOSFET, and there is only a single P region you can find. This region is called the part substrate. Then two highly doped N regions are part there. You can find. Okay. Okay. So there is only one single P region, and that you can find that is called substrate, and two highly doped N regions called the part defeat in the part lightly dot P type substrate actually. Okay, this is N and this is part N, but here you can find. Yes. Okay. See here. So there is only a part. I told about all the details here. So you can, here also I told a thin insulating gate layer of silicon put at the part gate, so that the gate became part isolated. Okay, and there is also a thin layer of aluminum is also formed over the part the layer of silicon oxide, and the metal layer covers the part entire channel region, and it forms the part gate G actually. So the metal area of the part gate is a conjunction with insulating oxide layer of silicon oxide, and the semiconductor channel forms a part parallel plate capacitor. Okay. Then coming to the part operation of the part N channel enhancement type MOSFET, here you can find. So this is a part actually part N channel FET. Okay, this is a part P substrate, and these are all part because as I already told the part this is a part metal oxide part contacts are there. So you can find also part this is a part source. Okay, this is a part drain, and this must be part gate actually. Okay. Okay. So now if the substrate is part grounded actually. So if we can say P type substrate is part make it ground, then what you can find, the positive charges on the per gate induces an equal negative charge on the substrate side between the source and that of the part the drain region, and the negative change of the part electrons, which are minority carriers in the P type substrate, forms an part inversion layer. As the positive voltage on the gate is increased, the induced negative charge in the semiconductor increases. Hence, you can find the conductivity increases, and the current flows from the source to that of the per drain through the induced induced channel actually. Okay. So this is the part idea about the part working construction of part N channel MOSFET here. Okay. Similarly, that we can go for the part enhancement type. Okay. So domain characteristics, so the drain characteristics actually first the part the drain characteristics. The drain characteristic of the part N channel enhancement type part MOSFET is shown in the figure. You can see. Just you can mark the part difference. At that time there is a part there is some sudden increase, but here you can find saturate actually. Okay, the drain characteristic of the part N channel enhancement type MOSFET is part shown in figure, and here you can find the transfer characteristic. You can find this one. Okay. See. Then okay. So the transfer characteristic you can find. So the transfer characteristic of the N channel enhancement time MOSFET is part just like a positive slope, increasing positive slope actually. And here you can find, so with increase of the part gate source voltage, you can find that ID current is part simple increases as per the equation, that is a part ID SS is equal to IDS into 1 minus e to the power EV by a part KT. So here for the same formula also can be applicable here. Then depletion type MOSFET you can find this is also classified into two types. One is called N channel depletion type, other is called P channel. Okay, N channel depletion type MOSFET you can find. The construction of our N channel depletion MOSFET is as shown the part figure, where an N channel is diffused between the part source and the drain and to the part basic structure part MOSFET here. You can see the part diagram. So this is a part P type substrate. The part N channel part small drop that is happened in the part surface. Okay. Okay. Just you can see this is a part the source, this is gate, and this is that of the part drain. Okay. Now you can find actually, so this is the part the symbol of N channel and also the enhancement type P channel part N channel. Okay, so when VGS is equal to 0 and the drain D at the positive potential with respect to that of the per source actually, you can see when VGS is equal to 0. Okay, you can see when VGS is equal to 0. Okay, the drain D at a positive potential. Okay, with respect to that of the source, and the electron are the part measured carriers flow through the per channel from source to that of the per drain actually. So what happened when I can put the per gate source voltage is 0. Okay, the drain at a positive potential, the drain is at a part positive potential with respect to that of the part source. So the electrons as the part majority charge carriers flow through the per channel from source to that of the part the drain, and therefore you can find the conventional current ID flows through the channel from drain to that of the part source actually. Okay, then you can find if the gate voltage part made negative. Okay, okay. See students, hello. Yes.
Yes, sir.
Here just I made one thing. Actually, I point out here actually one thing. All of you can mark if the gate voltage part made negative. So actually, we can operate under three different conditions actually. So if the gate voltage part made negative, positive charge consisting of the holes is induced in the part channel through SI3 the part the insulated gate capacitor. Actually, what you can do, so this is the part gate and this is the part insulated part. Actually, silicon oxide is a part maintained here. So the gate voltage made negative, positive charge consisting of the hole is induced in the part channel. That means if we can say this is a part positive, then immediately the part negative charge carrier will be part simple induced due to the part induction process actually. Okay, so the introduction of the positive charge causes deflection of the part mobile electron in the channel. Remember, the introduction of the part positive charge causes the deflection of the mobile electron in the channel. Thus, a deflection region is part produced in the part channel actually. So the shape of the part deflection region depends upon the part the voltage that we applied at the gate and also at the part drain, at the drain source. Okay. Hence, the channel will be part wedge shaped as shown. So you can see the channel is a part a wedge shape because all these part positive charges are get accumulated depending upon the part VGS value and also the part VDS value. Okay. So uh, now, when VDS is part increased, means drain to source voltage increase, the ID current became part increased and it becomes a part practically part constant at a certain value of the part VDS actually. Okay, and this is called the part pinch of voltage. Listen, when VDS is part increase, drain to source voltage will increase, then ID increases and it becomes practically constant at a certain value of the part VDS, and which is called a part pinch of voltage. Okay, so the deflection MOSFET can be also can be operated in an enhancement mode, and it is only necessary to apply a positive gate voltage so that the negative charges are induced into the part N-type channel. Hence, the conductivity of the channel is increases
and also ID is also part increases here. Just you can see that depending upon the part this VDS value and also the also part VGS value, we can also increase or the decrease is the part that enhancement charge on the channel. Okay, so now drain characteristics of N channel depletion type MOSFET. You can see VDS and also the part ID, and we are just increasing the value. Just you can see this is we are given the part gate source voltage +1 voltage, then 0 volt, then -1 volt, -2 volt, -3 volt. That means when you are starting from the part -3 volt to -2 volt, that the drain current is gradually part goes on part increasing. But having this is the part this is the part nature of the part current are the ohmic region, and this is the part saturation current, and you can find this ohmic current actually goes on part increasing with a part positive slope actually. Okay. Similarly, we can draw also the part transfer characteristics which have the part. It is also this BP value is also goes on part increasing, because when you can increase it part negatively towards zero, then this the drain current is also part increases and have a part maximum value at a particular at the zero voltage here. Okay, so then comparison of the part MOSFET with the part JFET. In enhancement and the reflection type of MOSFET, the transfers electric field induced across an insulating layer deposited on the semiconductor material, controls the conductivity of the channel. All of you can see in enhancement and reflection type of MOSFET, the transfers electric field induced across the part insulating layer deposited on the semiconductor material, which controls the conductivity of the channel. In the JFET, the transverse electric field across the reverse bias, okay, PN junction controls the conductivity of the per channel. Then the gate channel leakage current in a MOSFET is of the order of 10 to the minus 12 ampere. Here, hence the input resistance of a MOSFET is very high in the order of the per 10 to the 10 to 10 to the 15 ohm. Then the gate leakage current of JFET is of the order of 10 to the minus 9 ampere, and its input resistance is of the order of 10 to the power 8 ohm. Similarly, the output characteristic of the JFET are flatter than that those of the part MOSFET. If you can see actually for this output characteristic, so in case of JFET they are part more flatter as compared to that of the part MOSFET here. Okay. Hence, the drain resistance of a JFET is 0.12, that is 1 mega ohm, which is much higher than that of the part MOSFET actually. Okay. JFET are also simple operated only the part deflection mode, and the deflection type MOSFET may be part operated in both the deflection and also the part enhancement mode. Okay. Then you can find, and these are all comparison that you can see. So comparing to that of the JFET, MOSFETs are also easier to fabricate, and MOSFET is very susceptible to overload voltage, and also that of the part needs part special handling during your part installation. So it get the part damaged easily if it is a part not uh, is properly handled actually. Okay, so then MOSFETs are widely used in part digital VLSI circuit than that of the JFET because of the part the above advantages. Now I can go to the part small signal model of the part JFET. As like that we can on the previous section that we got actually the drain current as a source of your part VGS and also function of the VGS and also VDS. Okay, so here I have written from the drain and the transfer characteristic of the field effect transistor, we can say that the drain current of a FET is a function of drain voltage and also the gate to source voltage. So if both the per gate and drain voltage are varied, the change in the per drain current is given approximately by the two terms in the Taylor series for expansion of equation 1. Okay, so in small signal rotation you can find this into del VGS plus for delta ID by delta VDS upon delta VDS here. Okay. Now delta ID is equal ID and delta VG is equal VG. If we can put the for actually DC value, okay, then this equation 2 can be changed to your for ID is equal to GM del VGS. This is 1 by RD into for VDS here, where the transaction GM, you know, delta ID by for delta VGS, or that is delta ID by delta VGS, or ID is equal for VGS. Okay. Similar the per drain resistance RD is also part given as part like this. Okay.
and similar amplification factor is also part given as part there, but mu is equal to RD into a part GM here. So a small signal model for FPT in common, so uh, yes, in common source configuration can be satisfy equation 3 can be given as you can see here. This is for RD, this is part the part GM and VGS, that is mu. Okay, this is part gate, this is source. So that's you can find from the drain to that of the part current is flowing to the part this part through this connecting wire. Okay, and the part VDS here, and this is the part source of electricity. Okay, this is the part simple the uh, characteristic of the part. Yes, you can say. Okay, so the characteristic of the but this FET in common source configuration. Okay, and this actually you can find here. This low frequency model for FET has Norton's output circuit with a dependent current. Here you can find the current term here. Okay, current generator whose magnitude is proportional to that of the gate to source voltage. And you can find that's a current I proportional to the part. This is a part simple your part. Yes, you can find source voltage and also proportional the gate to source voltage, and the proportional factor is the part transfer terms, the trans conductance of part GM. The output resistance of part RD, and the input resistance between the part gate and the source is part infinite, since it is assumed that the reverse bias gate draws no current. For the same region, the resistance between the per gate and that of the per drain is assumed to be per infinite. So, while you can compute actually all these part JFET and part MOSFET, you must have to get the per ideas. Actually, the different parameters or the factors which are influencing actually the flow of the current through the JFET and also a MOSFET, and due to their part disadvantages, this MOSFET actually having the part is the enhancement type and also the part depression type. So you can find the most of the cases the depression type is part more effective as compared to that of the part depression type. Okay, so this is all about your part JFET and also the part MOSFET, and I think that I have completed that of your part the past that and also the part diet and all the things completely here. Okay, hello,
Yes, sir.
yes,
Yes, sir.
uh, okay. So now is this notice clear to all of you?
Yes, sir, noticeable.
Hello? Yes? Hello?
Hello. Yes, sir.
Hello?
What did you ask? Note is
I'm
visible to
asking,
us.
is this notice clear to all of you?
Yes, yes. It's clear, sir.
Okay. Now let me go to is now the part this slide is visible to all.
Yes, sir,
Yes, sir.
visible.
It's visible.
Hello?
Yes, sir. The slides are visible.
Okay. Just to see whether this is actually moving or not.
Yes, sir. It's moving. Yes, sir.
Okay. So now I'm going to the part the second or the part other part actually. This is called the part introduction to part amplifier, and in this amplifier we'll discuss actually the different type of amplifier like class A, class B, class C, class AB. Okay, and also the part their comparison, and we'll discuss in the part details actually the different applications of the part this part amplifiers. Okay, and finally you can go to the part actually the different feedback circuit and their comparison bandwidth and all details actually you can complete it we can complete uh, in this discussion actually. Okay, so let me first actually go to the part actually to amplifier, that is called amplifier. So all of you know, so what is an amplifier? You can see an amplifier is a part electron device, okay, or a circuit which is used to increase the part magnitude of the part signal of the applied signal applied to the part input actually. Okay, basically we can actually enhance the part strength of the part any input signal. So the signal may be a part picture, may be a part simple sound, or maybe part any type of electronic part sensing signal actually. Okay, now this amplifier can be thought as a simple box or a block containing the amplifying device such as a bipolar transistor. So it may be a bipolar transistor, it may be a PT, or it may be op-amp, which has two input terminal, okay, and two output terminal. Okay, that is the two input terminal and two output terminal, with the output signal being much greater than that of the part input signal, and which has been regarded as amplifier. You can see one amplifier circuit means a block, simple a box, or that may be that blocks may a block, or that block may be for JPT or a field effect, or this is a or BJT, or maybe for op-amp. It has two terminal, two input terminal, and one output terminal, and whatever the signal that we find, that is get amplified as compared that of the per input. Am I clear to all? Hello.
Yes, sir.
Yes.
Now, so what is an for ideal amplifier model? Okay, you can see. So the amplifier so the amplifier simple differentiate between the part input and also the part output signal, which is actually known as the part gain of the amplifier. That means, so if this is a part simple amplifier, this has the part to input, and this is also part output here, and this is a part signal output and this is signal input. So basically, whatever the part amplified portion that we are getting, we turn with the actual part gain. Okay, so there are part many forms of electrical circuit classified as a part amplifier, from operational amplifier and small signal amplifier up to the large signal and power amplifier. So the classification of an amplifier depends upon the size of the signal, large or small, its physical configuration, and how it processes the part input signal. That is relation between the input signal and current flowing in the part load. So this type or classification of an amplifier is given on the part in this table you can see here. So this is the part simple, the different part amplification, okay, or I can say here depending upon the part actually that part is the operation and also the part input and output. See here, so here the types of signal, there is small signal, large signal. So type of configuration part you can see is a common emitter type, because you have seen the part transistor, common emitter, common base, common collector. I put the part type so transistor as a part different amplifier like common emitter, common base, common collector. Then classification is a part class A amplifier, class B, class AB, class C, and the frequency operation is for direct current. This you can operate over class A, then audio frequency for the class B, and also a radio frequency for the class AB, and very high frequency, ultra high frequency, and small high frequency signals we can use in class C actually. Okay, now I'll be come to the part one by one, but before going to that actually you can see
So these amplifiers can be thought as a simple box or a block that contain the part amplifier device such as bipolar transistor, a FET and operational amplifier, which are two input and two output. I've already told you. Okay. An ideal signal amplifier will have the three main properties. One is called the input resistance, that is R in, output resistance R out, and of course amplification known as the part commonly gain. Okay, that is denoted as the part A. So no matter how complete an amplifier circuit is a part general amplifier model, that still can use to show the relationship between the part these three property. That means we can connect the part both the input and also the part this output through the part gain actually. Okay. So now, so we'll be part basically first so this all the three slides are I'm discussing about a part simple common amplifier, but now we can go to discuss actually a part power amplifier. The small signal power amplifier is generally referred to as voltage amplifier because they usually convert a small input voltage into a much larger output voltage. Sometimes an amplifier circuit is required to drive a motor or feed a loudspeaker. For this type of amplification, where high switching current are needed are called power amplifier. Okay, that means here you can consume the part more power as compared to that of the part general amplifier here. Okay, so the power amplifier, simple the name suggests, the main job of the amplifier is part the larger signal amplifier is to deliver power to load, and as we know from the above, the product of the voltage and current is applied to that of load with output signal power being greater than that of the part input signal. That means here what you can find, the power P is equal to power output, you can get the product of the both voltage and current, which has part much higher as compared to that of the part input signal here. Okay, or input power. So as compared to input power, you can get the part more higher output power here. Okay. Then the power amplifiers can be classified into different type like class A, class B, class AB, and part class C amplifier here. Okay. Now these are the type. We can see first we can start with the part class A amplifier here. Okay. All of you can see. So this is for class A amplifier. So why it is called class A? If the collector current flows all the times during the full cycle of the per input signal. See, what is the meaning of a cycle? So cycle means then one upper half and other is the part lower half. So that's upper half and the lower half is called a part a complete cycle. So in class A amplifier, if the collector current flows all the times during the full cycle of the input signal, the power amplifier is known as class A amplifier. All of you remember. So if the part this input signal will flow throughout the part the entire cycle, we call part a class A power amplifier. It is less used for higher power output stages as it has a poor efficiency. Okay, you see, it is very less used, and since its efficiency part very part less actually. The purpose of the class A bias is to make the amplifier relatively free from the noise by making the signal waveform out of the region between 0 to 0.6 volt, where the transistor input characteristic is part nonlinear. That means we can say here, the as it is a very part the it is operating the part in the noise making a signal waveform from this 0 volt to 0.6 volt. So it is morely part effective in case of the part this for the nonlinear, as and since we are particularly using part transistor for this class A amplifier, you can see in the diagram this is part simple NPN transistor. The collector region part coupled with the part simple the transformer, and this is the part simple the output or the load, and it has the part resistor R1 R2. So the input is applied through the part a capacitor, that is C in, and this is the part emitter bias resistor here, and this is also part capacitor emitter or emitter capacitor, which is get actually always to be part forward biased here. Okay. Now, so the resistors R1 R2 and RE. Okay,
Okay, but see the resistor R1, R2, and then RE. Okay, forms the voltage divider biasing circuit, and this sets up the load line exactly at the per center, and the transistor works as a per amplifier. I told the part you can see R1, R2, RE, and also the separate part. Yes, this forms a part simple a voltage divider circuit. Okay, similarly, two capacitors C in CE are called coupling capacitor. C in and CE are called simple the part coupling capacitors. C in couples the part input signal to the base. You can see C in part couples the part input signal to the part base here. Okay, of the transistor, and CE couples the load resistance to the part output here. Okay, so the C is called the bypass capacitor. Why? Because it is simple bypass the voltage drop across the emitter resistor RE, and this results in the voltage gain of the amplifier here. So this is for circuit description of the part class A amplifier. Then you can go for the class that is characteristic of the class A amplifier. So output current flows for the entire cycle. You have seen, because that is why it is termed as a part class A amplifier. Its operation of amplifier restricted to small central region, that is a part linear region. Output same as that of the input, since the part load point is exactly at the center. Okay, then you can find AC output power for active transistor is less as compared to class B and class C, and overall efficiency you can find that is equal to AC power, okay, delivered to the load by for DC input power, and you can get the part efficiency only for 25% of the total input signal. So that is why it is not actually part more effectively used in the part in the circuit or making part any devices. Okay, so these are the parts some limitations you can find. It has low efficiency because the transistor is always conducting, leading to the continuous power dissipation, high power consumption, heat generation, large and bulky due to the part need for heat sink. Okay, these are the some of the limitations of the part class A amplifier. Similarly, we can also move to now class B amplifier. Whenever the collector current supplies simply throughout the positive half cycle of the input signal, then this is called the part class B amplifier. All of this see, we are when you're discussing class A, that we told that part this class A amplifier only operate for both the uh, uh, positive and negative cycle of the part input AC, but here you can find the collector current supplies simply throughout the positive half cycle of the input signal, but not the part negative half cycle. A class B amplifier uses two transistors, each conducting for half of the input signal. I'll just let me show you. You can see this is a part two transistor. They are coupled. So one transistor of part operate for one half cycle, okay, and other transistor can also operate for the other half cycle. You can see this is a complete cycle input or complete input cycle, okay, but this is for the upper is positive, lower is for negative. So naturally, if this transistor can operate for the positive half cycle, then this so if this transistor operate for the negative half cycle, then this transistor operate for the part positive half cycle. And you can see, so when the negative half cycle operate, okay, it produces a part a positive half cycle amplified one here, and if it is a positive cycle operate, here you can produce a part negative cycle. Okay, so that's why I told it here. Yes, so class B amplifier uses two transistors, each conducting for half of the input signal cycle, that is 180 degree, and class B amplifiers uses two or more transistors biased in such way that each transistor only conduct during one half cycle of the part input waveform. Okay, so this is the part, and that is why this class B amplifier is sometimes termed as push pull. So one is pushing, other is get pulling. Okay, so push pull amplifier use two complementary or matching transistor, one being an NPN transistor. You can see one being an part NPN transistor.
Our screen is not visible.
Yes. Hello.
Yes, yes, sir. Now it's visible.
I'm audible now.
Yes, sir. You are audible now.
Okay. Okay. See here. So as this is simple termed as the part push-pull amplifier. So we may part so in a push-pull amplifier we may be talk about one NPN transistor and other may be part FPNP type transistor. Okay, and when they get coupled, na, you can get the part. Yes, just I told as like when you can operate one transistor operate for the positive and the other for the negative half cycle. So the output will be basically is actually you can see if we compare for this is the input and this is the for output, it is exactly part 180-degree phase change here. Okay, so this results in one transistor only simplifying one half or 180 degree of the input waveform cycle, while the other transistor amplifies the other half or remaining 180 degree of the part input waveform cycle, with the resulting two halves being put back together again at the output terminal. Okay, just you can see this positive half cycle appears as a negative half cycle, and this negative half cycle is again appears as a part positive half cycle, just like a part a push and also back to each other, or like a part push pull. So then the conduction angle for this type of amplifier circuit is only 180 degree or 50% of the part input. So naturally you can see that in class A amplifier you are getting 25%, but in class B that you are getting part 50% of the input signal. So this pushing and pulling effect of the alternating half cycle by the transistor gives this type of circuit its amusing push-pull name, but are more generally known as the part class B amplifier. Okay, is it clear to all of you? Hello. Yes.
Yes, sir.
Hello.
Yeah, धीरे धीरे.
Again,
Yes,
I'm
sir. It
asking,
is
is it
clear.
clear to all?
Yes, sir. It is clear.
Yes.
Yes, sir.
Okay. Okay. Now, so these are the part some of the applications of part class B amplifier here, because I have described the part circuit, and so these are the part some applications, and these are the part some limitations that we can find actually. So while you discuss actually class B amplifier, you must find this amplifier may be for find application in RF transmitter, and also the audio amplification, telecommunication, power amplification, instrumentation, signal modulation, public address system, high efficiency system. Okay, so all the things you can find some of the applications here, and these are limitations. Actually, if you can go to the design of this amplifier, this is a complex biasing. Here you can find heat dissipation, high load, high quality matching required, limited fidelity, not suitable for the low power applications. Transistor matching challenges also sometimes require lack of galvanic isolation and may require additional circuitry. So these are the some of the part limitations that you can find in case of class B amplifier. Okay. Now you can go for the part class AB amplifier here. Okay. So here you can find means we can combine both the part A type and also the part B type here. Okay. show an amplifier that is used to overcome the crossover distortion. Okay, in the class B amplifier is known as a part class AB amplifier. All of you can see. Okay, okay. So what I told, an amplifier that is used to overcome the crossover distortion. Okay, in the class B amplifier that is simply known as the part class B amplifier here. So the combination of the class A amplifier and a class B amplifier gives the class FB amplifier, and it is designed to overcome and eliminate the disadvantages of the low frequency in class A amplifier and distortion in class B amplifier, and hence this name is a part class AB amplifier. Okay, so the circuit diagram of the class AB amplifier is a part source. It is also consisting of the part that two transistor, that is like NPN and also part PNP, and for to purpose the to solve the purpose of the class A and class B, we are also using the two diodes D1 and D2 through the two resistors. Okay, and this is the part input terminal and these are the part output terminal. Okay, now here the two transistor T1, T2 are the considered for the circuit design. The transistor T1 is NPN type, the transistor T2 is a part PNP type. These two forward bias diodes D1, D2 are connected in, you can see the forward biased. Two diodes D1, D2 are connected in series to control the variation of part variation of VB, that is emitter to base voltage. Okay, okay. Then you can find also here did the part temperature change as shown in the part circuit diagram, because as these two diodes are for simple contact for diode, so this may be also part sensitive to the part temperature change. The resistor R1 is connected in series with the part D1, you can see, and similarly that we can find resistor R2 is connected in series with the part D2. Okay, so now these are the parts, some applications of the part this class AB amplifier. You can find it is using TV receivers, radio receivers, CD player, okay, audio frequency amplifier, and also public addressing system. And but still there is some limitations you can find. Practically the efficiency of class AB amplifier is less when compared that to the efficiency of the class B amplifier. That means even if we can combine class A, class B, but efficiency you can find less as compared to class B. So construction the you can see construction of the circuit is complex, cost is high, inappropriate biasing produces spikes in the output signal. Okay, means a pulse like structure resulting in part crossover distortion. The same distortion is also but retained here, not it is part get clear. So that is why class B AB amplifier is also not getting much efficiency as compared to class B. Okay, now coming to a part class C amplifier, you can find actually but yes, class A amplifier is a type of amplifier where the active element conduct for less than one half cycle of the input signal. You see, class A amplifier having high efficiency, and it can be used for used in the for large cases. Okay, so less than one half cycle means the conduction angle is less than 180 degree, and its typical value is from 80 degree to 120 degree. Okay, so the reduced conduction angle improves the efficiency to a great extent but causes a lot distortion. So theoretical maximum efficiency of class C is about 90%, around 90%. Just you can see compare A, B and also AB, so its efficiency is about 90%. So in most of the cases it is to be part used. So the circuit diagram for this class C amplifier is for here, and the biasing resistor RB is used to pull the base terminal of the Q1 transistor further downward here. So the Q point means that this is a load point will be fixed to below the cutoff point in the part. This is load line. Okay, so depending upon the part load value or the load point, actually that is called load line, and this load line is nothing but the part reflect a particular voltage and the current. Okay, so where it can produce a part maximum efficiency, okay, that can be decided here. Now So as a result of the part, this load point transistor will start conducting only after the part input signal amplitude has increased above the base emitter voltage pulse plus the part downward bias voltage caused by the part biasing resistor. So this is the reason why the main portion of the part input signal is not present in the part output signal, which is appeared in case of the part the class C amplifier, but not in the part other. Okay, so this is the part main for circuit operations or the part circuit explanation for the class C amplifier here. Okay, now just if we can see this is our application the part class C amplifier here. Okay, we can use in many cases RF oscillator, RF amplifier, FM transmitter, booster amplifier. Okay, and also but it in the same time it has some limitations, but these all limitations are part we are ignoring because it has a high efficiency as compared to top the part other. Okay, and this is the part summary table. You can see this is class A B ABC conduction angle, and this efficiency, distortion, application part, some of the limitations you can compare as a part in a short, just for different type of the part amplifiers here. Okay, now after that we'll go to the part actually some feedback concept and also the part stability concept of the part amplifier here. Okay, so just introducing actually what is a feedback. See the phenomenon you can see here, the phenomenon of feeding a portion of the output signal back to the input circuit. That means whatever the output that we are getting, we are again feeding to that of the input. So which you call feedback. Okay, the efficiency results in a dependence between the output and the input of a and an effective control can be obtained in the working of the per circuit. So feedback is of two types. One is called negative feedback and the other is called the part positive feedback. So what is a negative or degenerate feedback? See, negative feedback occurs when a portion of the output signal is inverted and feedback to the part input. Just all of you see, when a portion of the output signal is inverted. If it is not inverted directly you can fade, then it will call positive. But if it is inverted, then that is called the part negative. Okay. If the negative feedback, in negative feedback, the feedback energy that measures in terms of voltage and current is out of phase with the input signal and thus opposes it. Okay. And negative feedback reduces the gain of the amplifier. It also reduces the distortion, noise, and instability. And this feedback increases the bandwidth and improves the input and output impedances. Due to these advantages, the negative feedback is frequently used in part amplifier. Yes. Hello. Yes.
Yes, sir.
Am I just
Yes, sir. You are
clear to all?
audible. Yes, sir. Clear.
Hello.
Yes, sir. It is clear.
Okay. Okay. Now, so what is the part effect of the part negative feedback actually? You can see. So basically, it is the part stabilizes the part gain. Stabilizes means it reduces the sensitivity of the amplifier to component variations and temperature change. Then it also reduces the distortion. Okay, improves the part bandwidth, reduce the part noise, and you can see a negative feedback when I have discussed. This is the part input and this is the amplifier. We got the part as a part out of phase. So always you can get the part out of phase output. And if the inverse, you can see if this feedback is directly fed to that of the part input. So it is simple opposes the part this input, then we call the part negative feedback. Okay, so just you can see the part diagram. It is a part negative feedback circuit. So its application you can find is used in the audio amplifier, operational amplifier, other system requiring high fidelity and the part stable performances here. Similarly, we can feed also part positive or regenerative feedback here. Okay, So positive feedback occurs when a portion of the output signal is fed directly without any part inversion. That means you can see the diagram. This is the output and direct.
এটা বড়
Yeah. Hello. Yes. Hello. I'm audible na?
Yes.
Yes, sir, you are audible.
Okay. Okay. So, you see, in the positive feedback, you can find actually that this in positive feedback, the feedback energy, which may be current or voltage, is in phase with the part input signal. You can see. Okay. So this is a part, though we are getting here the output na 180 degree, but we can directly part fed to the part input with the part same. You can see the with the part same phase with the input. Okay, like you can see the part positive half cycle, negative half cycle, negative half cycle. Okay, so this is the part benefit of the part this positive feedback. But most of the time we can give the part positive feedback, so we are not getting sufficient part actual output. Rather, we always put the part negative feedback. If you can put the part negative feedback to the circuit, then it is highly part actually highly appreciating. Okay, so because of the part these disadvantages, positive feedback is seldom employed in amplifier, but most of the amplifier uses a part negative feedback amplifier. Okay, so but the positive feedback is used in part oscillator. When we discuss, we can only discuss positive feedback oscillator, but you can go for op-amp, you can find the part negative feedback amplifier, and its effect is part it increases the gain, can cause the oscillation, and also the part is it has a part applications used in per oscillator, regenerative receivers, certain type of signal generator where control oscillations are per desired. So this is the part idea of the part positive feedback or concept of positive feedback here. Now you can see a comparison I put in the part negative feedback and also positive feedback. You can part nicely part look to this. Uh, Feedback energy is out of phase with the input signal. Feedback energy in phase with the part input signal. Gain of the amplifier decreases, gain of the amplifier increases. Gain stability is increase, gain stability part decrease. Noise and distortion decrease, noise and distortion part increase. Increases the bandwidth, decreases the bandwidth. Used in amplifier, used in part oscillator. Am I clear to all? Hello?
Yes, sir. Yes, sir, it's clear.
Indranil ji? Hello? Indranil ji? Indranil ji, hello? Am I clear to all? Hello?
Yes, sir, it is clear.
Yes.
Okay.
Yes, sir, very clear.
Hello?
Yes, sir,
Yes,
clear.
please interact actually.
Yes, sir, everything is clear, sir.
Yes, sir, it is very clear.
Okay. Now, so another factor is for stability. So stability is what? Stability in amplifier actually refers to the ability to maintain a consistent output. So sometimes you can find actually fluctuation. So that is why you are many of the part for operating many of the devices you are need a part a stabilizer. So to contain or to maintain the stability in the part supply, we must need a part stabilizer. Similarly, here you can also part in amplification we need a part stability or a stabilized output. So to maintain a consistent output without oscillating or producing undesired behavior, which is called stability. So what is the condition for stability or criteria? So first is part board port analysis, which analyzes the gain and the phase margin of the amplifier using board plot to ensure stable operation. Okay. Similarly, Nyquist criterion is also sometimes used to assess the closed loop stability of the amplifier system. And similarly, pole zero analysis also used to analyze the first stability. These are the part some condition that is used in for stability analysis. So what are the factors that are affecting stability? First is feedback network. The design of the feedback network significantly impacts stability, and improper feedback can lead to phase shift and oscillations. Similarly, component variations also affect the stability, power supply, and also parasitic elements. Okay, these are the first some factors which may affect the part stability. Okay, then I'm coming to the part bandwidth of an amplifier. What is the meaning of the part bandwidth? See that this bandwidth actually represents the amount of frequencies or the band of frequencies that the amplifier is most effective in amplifying. So from which value of frequency to which value of the frequency, that is called the range of frequency, or the difference in upper half frequency and the lower half frequency, we call the part bandwidth. Okay, so whenever that we're talking about any of the part, the signal, or that when you can talk about the broadband or the narrow band in your part mobile or in a part any device operation, you are asking about the bandwidth. Okay, so the bandwidth of an amplifier is the difference between the frequency limit of the amplifier, the maximum amount of the data transmitted over an internet connection in a given amount of time. Okay, the maximum amount of data transmitted over an internet connection in a given amount of time, which is the difference between the part upper and the part lower half frequency. And this range is for simple crucial for ensuring that amplifier can handle the required signal. Okay, reduces the part uh, okay, that reduces uh, yes yes, you can find this range of crucial for ensuring that the amplifier can handle the required signal frequency without the part significant distortion or loss of the part signal integrity. Okay, because stability bandwidth is the part such frequency which can be maintained any irregularities between the part the two range of frequencies. So upper limit of frequency if f1 and lower limit is part f2, then bandwidth I can calculate f1 minus the part f2. Okay, so this is all about the part bandwidth. Now we'll come to the part oscillator. Okay, so rectifier is a circuit simple which convert to part AC to DC, but in case of your foam you are using actually inverter. Okay, and that inverter is nothing but a part oscillator. So oscillator simple converts the part DC to part AC, and it is part simple maintain the part or it maintain the part this stability. Okay, throughout the part this consumption of the part energy from the inverter to that of the part supply. Okay, an oscillator can be defined as a static electronic device that produces sinusoidal oscillation of desired frequency. Oscillator converts direct current from a power supply to an alternate current. An oscillator circuit contains three basic units, such as your part. Yes, you can see a frequency determined network, usually known as tank or oscillator circuit. Either is a LC or tank circuit, an electronic amplifier, this one, and a part network provide to positive feedback. Okay, these the three components which are required for a part oscillator. Okay, and any of the part machine for the oscillator that we are using for battery purposes, you can find such type of circuit also. Okay, now positive or regenerate feedback criterion for sustained oscillation, or that is sometimes termed as your Bragg-Hessen condition. Okay, so in this figure this is a positive feedback circuit, already you got the ideas. Okay, so this is the part the gain of the amplifier is simple rare part denoted as A. The gain of the amplifier is the ratio. What is that gain actually? It is simple the ratio of the part output voltage to that of the input voltage Vi, and the feedback network extracts a voltage Vf, means a feedback voltage, that is beta V0. Okay, so beta is a part simple coefficient, V0 is from the output voltage of the amplifier, and this voltage is subtracted for negative feedback from the signal voltage Vs. That means the total input voltage I can write Vs plus Vf. So Vs means signal voltage plus a part, that is a part S V0, that is a part beta V0. The quantity beta is nothing, is called the part feedback ratio or feedback fraction. Okay. The output voltage V0 must be equal that of the part input voltage Vs plus beta V0 multiplied by the part gain A of the amplifier. That means output voltage nothing is equal to, that is gain into a part input voltage. So if we can solve it here, that is AVS plus A beta V0, and which is equal to part V0. So AVS is equal to V0 into 1 minus a part A beta, and V0 by Vs is equal to A by 1 minus A beta. So therefore, the gain of the amplifier with the feedback is given by F is equal to A by 1 minus A beta. Okay, all of you be clear first. Okay, and basing on this AB value, which is called the part, this when I can put A beta is equal to 1, that is known as what, Bragg-Husson criteria. What is the meaning of this Bragg-Husson criteria? It implies magnitude of the loop of the gain A beta is equal to 1. If it is equal to 1, then 1 minus equal to 0. So something by 0, then you can find that is a feedback gain is found to be part infinity. Okay. Second, you can find that what is phase shift over the loop is 0 or 360 degree. Okay. That also that indicates the part phase shift is 0 or 360 degree. Then frequency of the noise in the amplifier for which these criteria are satisfied is the frequency of the part oscillations. Okay, and by applying this criteria we can even find the values of transistor parameter like gain required for setting the part oscillation. So you may find a question, what do you mean by part? This part is a feedback criterion for sustained oscillation, and hence derive the part Bragg-Husson condition for sustained oscillation with a part suitable diagram. This is you can get actually in the part oscillator starting. Okay. Hello.
Yes.
Yes. So we'll stop it here today. Hello.
Okay, sir.
Hello.
Sir.
Okay, sir. We'll stop it here.
Okay, sir.
Okay.
Okay, sir.
So we'll also start continue from the this in tomorrow. Tomorrow. Okay. Hello.
Okay,
Okay,
sir.
sir. Thank you.
So tomorrow this time or in other time you can do the class,
This time, sir.
or this time.
Yes, sir. This time.
Okay.
4 p.m. sir.
Hello.
4 p.m. will be great, sir.
As not audible, but your voice is not audible.
Sir, 4 p.m. will be correct time, sir.
Hello.
This, sir, if you are comfortable with any other time, you can suggest also, sir.
Okay, let me talk with the part the coordinators. Okay. So I'll share this part notes to you. Hmm.
Yes, sir. Thank you, sir.
Yes, sir. Thank you.
Hello.
Thank you, sir.
Thank you,
Yes,
sir.
yes, sir. Please share that.
Okay. Okay. Today I'm not sharing. Don't worry. Okay.
And also the handwritten note, sir. The first one.
Yes.
Also the handwritten note. This PPT as well as the handwritten note. The first.
Yes. Yes. I'll share all the things. I'll share all
Okay.
things.
Okay.
Okay. Okay. Okay. You can now leave.